Hello everyone and welcome back again to the linear algebra component of the calculus and linear algebra series. Last week we finished off this topic of mathematical proofs. So we talked about how to construct mathematical proofs using some of the propositional logic we've discussed in previous weeks, as well as set theory. And this week what I want to do is I want to introduce you to the topic of complex numbers. Now some of you might have heard about complex numbers before and some of you might have even worked with them. But what I want to do is I want to introduce them in a very intuitive and geometric way that hopefully gives you a kind of broader feel for what complex numbers are and makes you realize they're not really complex at all. They're very much a very intuitive thing to work with. But before we kind of move to them, I want to motivate or start with kind of a motivating discussion about how we would start inventing number systems ourselves. So you've worked for much of your time with real numbers. This is a number system and you study this in depth in the calculus component of the course. But starting at the beginning, if we start with something, say, like the natural numbers, well, we think of them as natural because in some sense they count things. And I have kind of briefly have mentioned this in the set theory component, but if I wanted to construct the natural numbers, I very much can construct them in the way that I think about them as counting the number of elements of sets. That is, I think of as one actually is defined as the object that defines one element of a set, and two I think of as the object that defines a set with two elements in, and so on. That's how I can construct the natural numbers. They are constructed in such a way that they count elements of sets. So I start with, say, the natural numbers, and I've built them from the idea of sets. And I can think of addition in those natural numbers as somewhat like the union of sets, right? If I have a set containing two elements, and I have a set containing one element, the union of those sets is a set containing three elements. And that's kind of how I can think of addition in that way, as somehow kind of the union of sets. So this very much connects set theory with building number systems. But now I want to take a kind of algebraic perspective. And what I want to say is, well, using the natural numbers, I can write down a simple linear equation. And I could write something down, say, like x plus 2 equals 1. That's a simple linear equation that you've seen in high school before. And you know there are solutions to that equation. But if I take my perspective now that I'm only living in this universe where I consider the natural numbers to exist, there are no solutions to that equation because there are no natural numbers that solve the equation x plus 2 equals 1. So let's suppose now that I invent a number and I just define the solution to that equation to be minus 1. That is to say that I'm not assigning necessarily any physical relevance to this number. I construct that number minus 1 by definition as the solution to that equation. And it's maybe an important point here to make that it is not the role of mathematics to assign physical relevance to mathematical concepts. We're perfectly fine within mathematics with inventing our own mathematical concepts and mathematical structures. And it's actually a very difficult task to try and assign some physical relevance to those mathematical concepts. This is kind of a deep area and a deep question of philosophy that I don't really want to go into. But the idea here is that we have this equation, x plus 2 equals 1, and we define the solution to that equation to be minus 1. We don't worry at the moment what minus 1 is. Later on we realise, wait a second, we can assign a physical relevance to minus 1. And this is more commonly known as debt, right? We have debt in society. If I have kind of say minus £1 in my bank account, that means I owe someone £1. That's kind of how we assign these things. And it turns out without this invention of negative numbers, the entire world economy would collapse. So we start with this idea of an equation that's unsolvable. We construct an abstract idea that is minus 1. It's this solution to this equation that we don't have any relevance to. And then later on, we realize it has relevance to the real world. And in a similar way, we can construct the rational numbers in this way, right? If I have another equation, I can construct linear equations with integers in front of those linear factors. I could take something like, 2x equals 1, right? In my world of the integers now that I've constructed, there are no solutions to that equation. But I can define a half to be the solution to that equation. I don't yet worry about whether or not that half has a physical relevance. That's a very difficult task. I just define one half to be the solution to that equation. And then again, I go back again and I say, okay, well, actually it turns out that there is a physical relevance, right? Okay, I can think of one half, going back to primary school, as I take kind of one whole, like my one whole orange, I cut it in half, and I think of a half as kind of fractional amounts of wholes, right? I can think of rational numbers in this sense as fractional amounts of wholes. And then you kind of extend to your next case, which is the real numbers. Now, the real numbers are a little bit strange in this case because I can't write down, or I can't construct the real numbers purely from solutions to definitely not linear equations and not even polynomial equations. Because in fact, there are some real numbers that are not solutions to polynomial equations, and these numbers are otherwise known as transcendental numbers that you might have come across in the calculus component of the course. Some typical examples of those are things like e and pi. But I can realize that there are equations that don't have solutions in the rationals, something like x squared equals 2. We know that the solution to that, or we can define the solution to that to be the square root of 2. Or we can also define it to be minus the square root of 2, but we define square root of 2 as the solution to that equation. So in a similar vein, we can kind of construct the real numbers into solutions to these equations, or we can construct many of them as solutions to kind of polynomial equations. And then we end up with this concept of the real number line, right? We have this number line that you draw in primary school, and there's no gaps in that number line. And we've kind of assigned some physical relevance to most of our numbers. We've assigned kind of a physical relevance to the natural numbers as counting, the negative integers as like det, 0 is doing nothing. We've assigned like fractions as kind of fractional wholes. That's how we're thinking of them. Real numbers are a little tricky, and you see already we run into a problem about trying to assign physical relevance to something like the square root of 2. Does that really exist in the world? Again, it's not really the relevance of this course or mathematicians to discuss whether or not these things exist. You could, I guess, think of them in a geometric way. Say, well, there is a relevance to it. If I construct a triangle of 1 unit along and 1 unit up, then its hypotenuse has length square root of 2. And I guess that is some sense of physical relevance, but it's not in the same way as the others. But I kind of reiterate again, it's not the task in mathematics to assign physical relevance to abstract quantities. We can introduce and define these abstract quantities, and later on they might have some physical relevance. Now, what I want to do is I want to change your perspective and view all these numbers on the real number line in a different way. So rather than viewing them as counting or det or fractional wholes, all these other things, I want to view them, I kind of introduce these two different ways of introducing them as ways in which they transform the number line. And viewing them in this way is going to be particularly useful when we start introducing complex numbers, because what we will realize is that complex numbers are simply just an extension of this idea of transformations of the real number line. And it will be kind of very obvious what we can think of as I, which is going to be known as the square root of minus 1, in this way. So let's go to our kind of first animation here and think of it that. Now I call this thing the additive real. So here what I've drawn now is our number line that we've kind of introduced. You've seen this in primary school, and we have a second copy of our number line in red here. So we've got two copies of our number line on top of each other. And I want to, when I write here the additive reals, I said there was two perspectives in which I was going to introduce or kind of think about the numbers now. And this is going to be in an additive way. We're going to call this kind of the additive perspective. Now, what do I mean by that? So let's have a look here at the number 2. So we thought of the number 2 previously as saying that it counts a set with two elements in. But let's view it in a different way, and let's view it in the way that it transforms the number line above in a certain way. So we're saying, right, this red number line is kind of the numbers that we're going to select, and we're going to think of them in the way in which they transform our white number line above. So we think of the number 2 here as the thing that transforms the number line to everything to the right by 2. It shifts everything along by 2. So that is to say that we're thinking of the number 2 here now not as counting elements, but as the thing that transforms the number line to the right by 2. And this is when we think of it in the additive way. We say additive because you realize this is really just addition. What we've shown here is that what we do if 0 plus 2 is 2. That's exactly what we've got. Above the number 2 is the number 0. So let's look at another example here, returning back to the middle. Let's look at the number minus 2. How can we think of the number minus 2? Well, before we thought of it as det, but now let's think of it in this transformational way. It should be fairly clear now that thinking of it in this transformational way, it's the thing that transforms the number line above by shifting it to the left by 2. And again, we're just changing this perspective. Rather than thinking of it as det, we're thinking of it how it transforms the number line under addition. Right? In this case, we've got 0 plus minus 2 is minus 2. So that's exactly what we've got. Okay, so we can extend this as well, right? Easily to the reals. So here I've kind of got a kind of label above my arrow now to describe what the number is that it's pointing at. And as this arrow is going to move along now across all the real numbers, kind of smoothly across the real number line, we'll see how it transforms the white line above. So as it moves along, we see that what it does is it shifts the white line along by so many units of whatever that line is, or whatever the arrow is pointing to. So in that case now it's pointing to 6, so it shifted the number line along to the right by 6 because it's plus 6. So returning back to the middle and doing the same for the negative numbers, what happens is I move my kind of white arrow along smoothly along the negative numbers, that's going to be shifting my number line above in the left direction by however many units are that my arrow is pointing at. So my arrow is now ended up at -6 and it shifted the number line up by my -6, or it shifted it by 6 units to the left. That's what -6 is corresponding to. So how then as well could we maybe interpret addition? What does it mean, for example, to say 2 plus 3 equals 5? So let's look at the number 5 here. Well, what does 5 mean in this kind of transformational way? Well, we think of 5 now not as counting 5 things, but we think of it as shifting that number line above to the right by 5 units. So it does that. That's how we think of 5. And saying 2 plus 3 is 5 is the same as saying, well, let's take 2. That means we shift the number line to the right by 2. And then take the number 3. That means we shift again by the number line by 3. And we say that if 2 plus 3 is 5, that's the same as shifting all along by 5. And we can see that here. So that's exactly what addition is meaning in this transformational sense. We're saying that when we add two numbers together, that's the same as kind of doing the transformation corresponding to the first number and then the transformation corresponding to the second number. So in this case, the 2 plus 3 plus 5, 2 plus 3 equals 5 is saying that transforming 2 units to the right and then transforming 2 units to the right by 2 and 3 units to the right by 3. Oh, let's say that again. Transforming to the right by 2 units and then transforming to the right by 3 units is the same as transforming to the right by 5 units. So that's effectively what that's saying. But I said that we were going to introduce two perspectives here, so let's bring this back to the middle. And another perspective in which we can think about how the numbers act is not by addition, but instead by multiplication, right? We know that we can multiply numbers. So what does it mean in that setting? Well, now if I take the number 2, rather than thinking of it as shifting the numbers to the right by 2, I can think of this as stretching our number line above by 2. So in other words, I kind of fix 0 and I stretch everything out by a factor of 2. So in this case, where this is a second perspective, a second transformational perspective to take. The first one we had was of thinking it as shifting, but we can also think of it as stretching actions, and viewing these two things together will be really useful for complex numbers. And similarly, right, we could take another example here. We could take something like a half. What would a half do? Well, we think of a half rather than as a fractional whole, right? Like we did in the other setting, or in the initial setting, we think of it now as something that squishes our number line by a factor of a half. So we're really changing our perspective of how we view these numbers. But there's no reason why we can't change our perspective, because again, these are abstract things, and providing we view these things in this consistent way, that's perfectly fine. So now we're viewing our numbers in these transformational ways. What about something like -1 now? So when we viewed it as a transformation in this additive way, that shifted our number line to the left by 1 unit. But when we now think of it in this multiplicative way, what does -1 do? Well, we think of it as rotating the number line by 180 degrees. So that's now a kind of different perspective of thinking about -1. We can think of it in an additive way as shifting the number line to the left by -1 units, or shifting it to the left by 1 unit. Or we can think of it in a multiplicative way as rotating the number line by 180 degrees. Now, returning back to our middle point, as another example here, we can show that it does extend to the real numbers as well. So in this example, my arrow here is pointing at pi, and we want to see, well, how's that going to transform our number line above? Well, it's just going to stretch everything by a factor of pi, and we can see that that is exactly right there, because we see down below that 1 corresponds exactly to pi. In other words, 1 times pi is pi. Okay. So, like before, we had this interpretation of addition. What does it mean to say 2 plus 3 was 5, and we saw that was the same as shifting by 2 units to the right, and then shifting by 3 units to the right is the same as shifting by 5 units to the right. What does it mean in this multiplicative sense? Well, let's take something like 4. Well, we want to see that 2 times 2 is 4. We know this to be true. So we think of 4 as stretching our number line by a factor of 4, which gives the thing above. And then if we look at what it does now for 2, if we take the number 2, that stretches by a factor of 2. And then stretching by a factor of 2 again is the same as what it means to stretch by a factor of 4. So we think of multiplication in the sense as kind of multiple stretchings. And we see that 2 times 2 equals 4 is effectively all it's saying in this geometric view is that 2 factors of stretching by 2 is the same as a single factor of stretching by 4. And in a similar way, we can extend this to the negative numbers, right? So let's think about minus 3. How would we get minus 3? Well, we can construct minus 3 by doing minus 1 times 3. So if we start with minus 1, what does minus 1 do? That flips our number line by 180 degrees. And then we want to go over to 3 now. So what would 3 do? That means that we stretch our number line by a factor of 3. And that's exactly what we'd expect by an action of minus 3, right? We've got here that 1 corresponds to minus 3. In other words, 1 times minus 3 is minus 3. So we've that's where we're going to finish. And to reiterate what we've done here is that we've kind of introduced the numbers from this abstract point of view as solutions to equations. We found, or you've been kind of told in school a lot, about some physical relevance of these numbers, you know, in terms of counting and fractions, fractional wholes and debt, things like this. But there's another perspective that we can take on numbers, or at least 2 different perspectives we can take on these numbers. One in the way in which they act on the number line via addition, and that was via this kind of shifting left and right. And the second perspective was that of acting on the number line via multiplication, which was this kind of stretching and squishing action. So we can think of numbers equally in these 2 different ways. And both of those ways in which they acted on the number line were consistent with the usual addition and usual multiplication that we know. That was to say that if we did a shift by 2 units to the right and then another shift by 3 units to the right, that was the same as a shift by 5 units to the right. And similarly, something like a stretch by a factor of 2 multiplied by or done with a stretch by a factor of 3 is the same as a stretch by a factor of 6, which is kind of saying that 2 times 3 is 6. So you might think that this is very strange, but what you'll see in the following videos, that thinking in this way is going to be particularly useful when we start introducing something like I, which we will understand to be the square root of minus 1, which in turn tells us that I squared equals minus 1. And we've already seen that minus 1 we can think of in this multiplicative way as the thing that rotates the number line by 180 degrees. And thinking in this way, if I squared rotates the number line by 180 degrees, we can think of I maybe as rotating the number line by 90 degrees. And this is going to be kind of the key picture that we're going to take when introducing the complex numbers. So that's where I'm going to finish this video now. And I remind you to read the notes here and think about these in detail. And there's probably not really any questions that you can do yet in the module handbook tied to this, but this video was more of a motivation so you can see why the complex numbers have this kind of very geometric picture when we get to that in future videos. So thanks very much for watching and see you in the next video.